We'll go ahead and start with reviewing the activity that you just did out in the hallway. So, what were some relationships that you noticed between the Cartesian XY ordered pair and the polar R theta ordered pair? Were there any relationships that you were able to use so that you could find those exact values, Lily?
With those, you can use the arctangent to find the angle, and then solve for the hypotenuse of the triangle.
Excellent. The arctangent or inverse tangent of y over x, and then basically the Pythagorean theorem. And we're going to adjust it from what we saw in chapter 6 where we were using a and b for like the complex number or vector components. Sorry. We change it to x and y for the Cartesian coordinates. So we can say theta is equal to the arctangent of y over x, and r is equal to the square root of x squared plus y squared. And as I was moving around the different groups, I think most people got to the same answer. So if you have your activity out, number 3A, you should have said pi over 4 or 45-degree rotation. B was 2 square root 2, which is the square root of 8. And then in C, the polar coordinate would be 2 square root 2, comma, pi over 4, or 45 degrees if you use that. And then for number 4, if you run through steps 1 through 3, your polar coordinate should be 5, 127 degrees, or 5 and 2.215 radians. Was anybody able to do the bonus on the activity where you rewrote the first coordinate in a different polar coordinate?
What we did is we just added 360 to the degrees.
Yeah, so you guys had the polar coordinate 2 square root 2, comma 45 degrees, and then they just added 360 degrees, so then 2 square root 2, comma 405 is the same point on the polar grid. Did anybody else do a different one besides 2 square root 2, 405? Okay, we're going to see that pop up in an example a little bit later where you write out multiple representations. And one thing I'm going to say in my multiple representations is we're going to keep the angle between negative 2 pi and positive 2 pi, which would be negative 360 and positive 360. So while I agree with your guys' new polar point, works perfect, normally when I ask for multiple representations, I don't want that answer because 405 is outside of that range. Okay, so that's something we're going to see here in a little bit. Excellent. So if you would, you can choose to write this down if you like. You also might just be able to follow along. The next slide has some more information about polar coordinates that I'll ask you to write down. I'm just going to review really quickly the Cartesian coordinates. So these are the coordinates that you've been working with for a very long time. They're your XY ordered pairs. X represents a horizontal distance. If X is positive, we know to go right. If X is negative, we know to go to the left. And Y is your vertical distance. When it's positive, we go up. When it's negative, we go down. And there's that coordinate plane that we've been graphing probably since you learned how to graph. Okay. So these are very familiar to us, and we know how to work with Cartesian coordinates pretty easily. The polar coordinates are a little bit different. Of course, instead of xy, it's going to be represented as r comma theta. Theta can be given in radians or degrees. I don't care which one you give me. On a side note, I usually go back to radians. It's just common to use with polar coordinates in a math class. You're going to see radians quite a bit in the textbook. So that's kind of what I just go back to. But either one is acceptable. R represents a directed distance from the origin, and on the next slide I'm going to call the origin the pole. So it's the pole of the polar grid, the center of the polar grid. And theta is your directed angle from the x-axis, which we're going to call the polar axis on the next slide. We're going to give a specific name. Theta is just like all the other angles we've worked with in all of our other chapters that have involved trig. They open counterclockwise from the positive x-axis. You need to be cognizant of where your point will be, which quadrant it's in, quadrant 1, 2, 3, or 4. And I see as I walked around during the activity, most people were able to make that adjustment for that 127 degree angle. Okay, so good job. The picture for polar coordinates, and I know that's a little bit hard to see on this board, is that picture that if you flip over your activity, you've got some polar grids on the back of it. So like when we do our examples today, if you want to do your examples on those polar grids, you can use those for examples. Feel free to do so. The polar grid is not like something super terrible to draw. If I'm going to draw my own polar grid, I think the easiest way to do it is to start with a vertical and a horizontal axis. Okay, so find that center point, that pole, and then I just start with my concentric circles. And I pay attention to my problem, like how many concentric circles do I need? If I only need 3 because my radius is 3, I'm going to stop there. And then if you need those other angles that are represented by these red lines, you can draw them in. They're just the 30, 45, and 60 degree angles in each quadrant. So you can split them up. There's my 45, and here I'll get 135 and 315. And then I could do my pi over 6 angles and my pi over 3 angles. So it's not like it's a really challenging thing to draw. So if you need to draw it for any reason to plot points, you can do that. If you didn't write down the information from the previous slide, I would say you should jot some of this information down. Okay, so that you at least have this written down somewhere where you talked about polar coordinates. So again, this is just reiterating that piece. We've got r theta. R commonly is referred to as the radius. It just represents a distance from the pole, and it's a directed distance. Okay, so positive and negative mean 2 different things. And then theta is your angle to the polar axis. I went ahead and labeled the pole and the polar axis. Basically, the pole is the origin, and the polar axis is the positive x-axis. And then I highlighted or starred that note there. That's also in your activity, and I heard some groups talking about that as I was walking around outside. If r happens to be negative, then your point will be plotted on the line opposite, or the ray opposite the actual angle theta. So it's like if your theta was pi over 4, you would go in the opposite direction, that distance of your radius. And we'll do an example where we plot one like that so you'll be able to see it. Okay, but that's pretty important. So I'm going to do one example where I graph, and like I said, you can either draw your own polar grid in your notes, or if you want to use the polar grids on the back of the activity that are already there for you. I'm going to plot 3 points on the same polar grid right here. Okay. So I've got the polar point 2, pi over 3. And I recognize that to be my r theta. So on the polar grid, I'm going to first find the correct r, which is that circle or ring that has a radius of 2. So I'm starting from the pole, and I'm counting out the circle that has a radius of 2, so that's the second circle. I'm somewhere on this circle, okay, and it's going to be the angle that finally narrows down my actual point. So at 2 pi over 3, I should be in the first quadrant on the pi over 3 angle. I'm going to go ahead and label that number 1 for my first example. Take a moment and see if you could plot the next 2 points. See where you think they'd be, and then I'll graph them, and we'll see if we agree and if we have any questions. For example 2, I want to go out to the next circle with radius 3. So count out from the pole. So you're on the circle with radius 3. And then I'm somewhere on that next circle. And to narrow down my location, I've got the angle negative pi over 6. So I'd go to the polar axis, and then a negative angle would go clockwise, pi over 6. So my point should be in quadrant 4. Note that when the angle is negative, that just changes the direction that the angle opens, clockwise instead of counterclockwise. That last example, see if you got this one right. This is the one with the negative radius, so that goes back to the note that we talked about on the previous slide. If I were plotting that point, I'd be on the circle that has a radius of 3, so the same circle I was just on. And I want to go to the 240 degree angle, which 240 degrees is in quadrant 3. Okay, and I'm going to mark that with an X. But I actually don't want to plot my point right there because the R value is negative. So I'm going to plot my point on the circle with radius 3 in the opposite direction of 240. So that would actually be my 60 degree angle in quadrant 1.
When you're like marking that down, do you have to do the X?
No. No. Okay, so I would literally just see the point 3 on my polar grid. Are we okay with that? Does anybody have any questions or clarifications that they need made? Okay, so the next example is going to be a similar example in that we're going to plot this point 3 and 4 pi over 3. But we're also going to do that thing very similar to the bonus question on the activity that you're doing out in the hallway. Can you write that same point with different polar coordinates, but be in the same position? So we're going to call that multiple representations. Now, for multiple representations, remember I told Lily, your angle was right, 2 square root 2, comma 405. But in the future, we'll not want that answer because it's outside of 1 revolution. So we want to keep theta between negative 2 pi and positive 2 pi, or you can think about theta between negative 360 and positive 360. So I'm just going to go ahead and graph 3, 4 pi over 3. I'm on the circle, third circle out from the pole. 4 pi over 3 is in the third quadrant. So 1, 2, 3, right about here. There's my point. And I'm going to give you some time. I'm going to give you about 30 seconds on your own. Then I'll have you talk with the people around you. Can you come up with 3 different ways to name that point? It's the same point. And theta is between negative 2 pi and positive 2 pi. And test your skills there, and I'll have you check in with the people around you in just a moment. Please pick up one. Lean over, talk to the people around you. What are some of their ideas? What are some of your ideas? Can we get 3 additional points? I'll call on you here in just a minute.
I only got 1, and that was negative 3 pi over 3.
I got that as well, but I also got a 3 negative 2 pi over 3.
I think I got negative 3.
That's what I had. Because it says from 2 pi, from negative 2 pi to 2 pi. So I just like, so negative 4 pi over 3 is like right there. If you go the other direction, it's like right there, it's like 4 pi over 3. It's just remember from the unit circle.
Oh, no, this.
It configures
Oh, that's.
I don't even know when its birthday is.
Oh, okay.
You guys could just celebrate the anniversary of when you learned it. Trigger goals. Okay, Nick, do you have a multiple representation for us? Another polar point that works to get you in the same spot as that blue point right there.
Negative 3 pi over 3.
Negative 3 pi over 3. Okay, so let's check that one out. If I were to plot negative 3 pi over 3, I'd be going out to the third circle, and then pi over 3 is up here in the first quadrant, but I would actually want to plot opposite because of the negative radius, which will get me right back onto the blue point. Good, I agree with that one. Maddie, do you have a different one?
Sammy had one.
Sammy, you've got one?
I said 3 negative 120.
3 negative 120, which negative 120 is what in radians? Negative 2 pi over 3. Okay, so I'll put both of those representations. So go to the third circle, and then instead of going counterclockwise, go clockwise 120 degrees or 2 pi over 3, and sure enough, we're going to land right back on that same spot. And Ryan, do you have another one for us?
Negative 3, negative 5 pi over 3.
Good. Negative 3 and negative 5 pi over 3. So 3 tells us, or negative 3 tells us to go to that circle with the radius of 3. And then negative 5 pi over 3 would be to go clockwise 5 pi over 3, which will put us in the first quadrant where that x is. But the radius is negative, so we should go in the opposite direction. We'll land in the same spot. Excellent. Okay. So what I like about radians is that, notice we've used all the pi over 3s. 4 pi over 3, pi over 3, 2 pi over 3, 5 pi over 3. Some of them are positive and some of them are negative, but I know that I've used all 4 of them when I'm doing the multiple representation. So that's kind of nice if you're doing that type of problem, like if it's a pi over 6, you're going to use all 4 of the pi over 6 angles on the circle. If you're doing it like so that they have to be negative 2 pi to 2 pi. Okay. So I kind of like that. And then you'll also start to notice a pattern. There will always be 2 polar points that have positive radius, and then there will be 2 that have negative radius, and each one will match up with a positive or a negative angle. Okay. So you'll kind of notice a pattern there when you're doing the multiple representations. Good. Okay, now this slide is basically the same information that you uncovered in the activity that we've been uncovering with trigonometry in chapters 4, 5, 6, and now 10b. To go from rectangular coordinates x and y into polar coordinates r and theta, we need to know r is equal to the square root of x squared plus y squared. And we need to know theta is equal to the inverse tangent of y over x. Okay. So I've lost count of how many times we've seen that same idea over and over again. Okay. Nothing brand new. The other one is to go from polar to rectangular, so r and theta, to get into x and y. We have done this before, and most recently in chapter 6 with the vectors and the complex numbers. Think about your horizontal and vertical components in vectors when you're using magnitude and direction angle.
Is it like x equal to r times cosine of theta?
Yes. And y is sine. So x equals r cosine theta and y equals r sine theta. You know, I'll say if you can do theta on the unit circle and give me exact values, you should. Just like we've always done in the past. If the angle that's provided for you is not an angle from the unit circle, then by all means plug those things into the calculator and get a decimal value. Okay, so I'm going to put up two examples, and I'm just going to leave you guys some time to see if you can convert them. One's going to be converted into polar, and one's going to be converted into rectangular. First one is convert 0, 2 into a polar coordinate, and the second one, convert 2 pi into rectangular coordinates. So I'll give you some time to jot those down and give it a go. Feel free to talk to people around you if you need to. Okay, I'm going to put up my work and we'll see if you agree or have any questions. These are rectangular points, x and y, so I need to find r and theta. That would be the square root of 0 squared plus 2 squared, which is the square root of 4 or 2. And then theta is the inverse tangent of 2 divided by 0, that's y over x. We talked about this last chapter. 2 divided by 0 is undefined. Our calculator will not evaluate that for us, but the unit circle, we know where the undefined angles are. They're on the vertical axis, so 90 degrees or 270. Figure out which one matches your point, 0, 2 would be 90 degrees. So you could say 90 degrees or pi over 2 for your angle. And then write that as a polar coordinate, 2 comma pi over 2, or if you have 90 degrees, that's also okay. Are we feeling all right with that one? Okay. And then down here, this one is actually very easy. Okay, you're just going to do x equals the radius times the cosine of pi, and y equals the radius times the sine of pi. This one happens to be for my unit circle, so I don't even really need my calculator here. The cosine of pi is -1, and the sine of pi is 0. So then I'm going to get -2 comma 0 for my x and my y. Note that both of the angles, when you look at the polar coordinates in these examples, they're quadrantal angles, 90 degrees, 180, 270, those types of things. If you have an angle in your polar point that is quadrantal, then one of your rectangular coordinates must be equal to 0. Because then you're going 0 left or right, or 0 up or down, and you're staying on the axis. If it's not a quadrantal angle, then both your x and your y would be some number value to get you off the axis. Okay. Any questions about converting points? Okay, last thing that we want to talk about, and this is going to be like, I think when you do your homework assignment, this is going to be the biggest struggle. Okay, is converting equations. Yay, converting equations. You make me think you're not listening to me. Who don't want to listen to me? Such interesting mathematical things to say. Okay, so polar to rectangular and rectangular to polar. Those are the two ways we can go. Now, obviously, you'll be able to tell which equation you're working with. Does it have r's and thetas to start with? Then you're going from polar to rectangular. Or does it have x's and y's to start with? Then you're going into polar. I'll say rectangular to polar is probably the easier of the two. Okay, this involves a lot of just plain old substitutions. So things that you can substitute when you're given something in rectangular form. Like, you know x's are cosine theta. You know y is r sine theta. Okay? And there are some other things that you know. If you think back to that r equals the square root of x squared plus y squared, if you think back to geometry, that's very similar to the equation of the circle. So if you happen to see an x squared plus y squared, you can also replace that with r squared. And that would be just changing it into polar. Okay, so there are some other things that you can use to change. If you saw like a y over x, so a y divided by x, you could put in a tangent of theta, which would again be changing it into polar because it'd be in terms of theta. Okay. Generally, I'll say this: you most of the time want to solve for y, okay, but sometimes you'll have to solve for x. Oh, sorry, that's the wrong one. That should be on the previous one. Sorry, we want to solve for r. So we're going into polar. So generally you want to solve for r. Sometimes you'll have to solve for theta. And the sometimes theta would be like when you don't have an r to solve for. If there's no r in the equation, then you're going to have to solve for it. Okay, but you usually want to have it look like r equals. Polar to rectangular is a little bit tougher. If you read in the textbook, one of the sentences that they say about this conversion is converting from polar to rectangular requires some ingenuity. Okay, well that's not very helpful, right? So it's like one of those things like just experiencing it and doing it a few times and coming up with different ideas. Like, I can't do all of the examples today for you. So you're just going to have to try and think about it. But you're going to be thinking about some of these same things. So remember, like r is equal to the square root of x squared plus y squared. You know that r squared is equal to x squared plus y squared. You can be looking for different things that you could sub in so that it goes back to rectangular. Okay, so you're going to be trying to put in the x's and the y's. So you're going to be looking for r cosine thetas. You're going to be looking for r sine thetas, because those go back as x and y's as well. Here you're going to solve most of the time for y. Sometimes you got to solve for x. And sometimes for that x squared plus y squared. Anytime it's a circle, if you've got x squared and y squared, you're probably just going to leave it alone. You're not actually going to go through and solve for y there. Okay, so now I'm just going to do some examples. I'm going to start with x equals -4. And that's clearly in rectangular form because it has an x, so I want to change it into polar form. So I'm thinking about all this stuff I know. What could I do in terms of substitutions? For cx, I could write r cosine theta. So r cosine theta is equal to -4. Okay. And generally I want to solve for r. So how would I get r all by itself? Divide by the cosine of theta. And a lot of times I get students, especially when we're first starting out, we'd be like, okay, this is good, -4 divided by cosine theta. I also kind of agree with that, but think back to chapter 5. If you're dividing by cosine theta, what are you multiplying by? Secant, the reciprocal identity. So if you have cosine theta in the denominator, you can pull it into the numerator with the reciprocal function. So r is really -4 secant theta. You got a question? Just excitement about what you're doing? I get it. It's kind of weird and like, you're like, what am I even doing, right? Like, it's just going to take some time to kind of get used to that. Let's look at another one. So my next example is x squared plus y squared equals 25. Again, this is in rectangular form, so I want to change it into polar form. So I want to have r's and thetas. I know from geometry, x squared plus y squared is really equal to r squared, the equation of a circle. So where I see x squared plus y squared, I can just write r squared equals 25. And can I do anything to solve for r right there? Square root both sides. So r is 5. Now, this one's an easy one for you to think about in terms of what that picture is. X squared plus y squared equals 25 is a circle with a radius of 5 and a center at 0, 0. R equals 5. Think about if you were to do that on the polar graph. You go out to the circle with a radius of 5, and there's no angle, so you just keep going around it, and you've got a circle with radius 5 around the pole. So they're the same graph. Try your homework. Bring your questions. We'll probably end up doing several of those examples tomorrow at the beginning of class for more practice.
Let's practice.
Mm-hmm.
Wait.